So we are going to start our conversation about calculus by investigating the concept of instantaneous rate of change, right? So this should be a bit of a nonsense idea if we remember what a rate of change is. So let's start there. What do we mean by a rate of change? Well, obviously we mean something's changing. And when we talk about a rate of change, what we're actually talking about is two things changing. We're talking about the relationship or the ratio between how one thing changes relative to another. The most common one is probably speed. Speed we can think of as, right? You've probably seen something like distance over time. What we really mean when we write this, let's write this a little bit better. We really mean the change in distance over the change in time, right? So if I tell you that I'm traveling at 10 miles per hour, what I'm telling you is that if time changes by an hour, if we move forward 1 hour in time, my distance will change by 10 miles. If I tell you I'm moving 3 meters per second, I'm telling you that if the time changes by 1 second, my distance will change by, what did I say, 3 meters, right? It doesn't have to be. This is a really common one. Another example could be something like if you're running a factory, if you're selling some product, you might know that for every item you sell or produce, you get $2 in profit. So you have profit per item, right? Or if you've gone hiking and used an elevation map, you might know if we move forward by a mile, we're going to gain 1,000 feet, right? So you know that if you change your distance horizontally by a mile, you'll change your distance vertically by 1,000 feet, right? In each of those cases, we're getting a change in one quantity per a change in the other. Speed is a really good example for us, right? So we often will use this notation delta. It's a Greek letter, and we use it to indicate a change, right? So change in distance over change in time, okay? So now, what do we mean when we go to instantaneous? Because instantaneous, right, sticking with the speed idea, means how much does our distance change if time doesn't change at all? It's an instant. There is no interval of time, right? So there's obviously something wrong with this statement that we need to explore, at least something unclear about this. So let's think about it this way. Suppose we drop an object from a height of 490 meters. Okay, so we have an object, let's pretend it's a marble, say. We have it 490 meters, and we're going to up in the air, and we're going to drop it, right? So it's starting held, and I let go of it, and it begins from not moving. It starts to fall towards the ground. This can be a very complicated problem if we worry too much about things like air resistance. Let's pretend it's in a tower that has been evacuated of all air. So we've got a vacuum. So it's just going to fall under the force of gravity. It can be, physics gives us a model for this falling. So I can give this formula. This is going to be the height in meters of our marble at time t in seconds, right? So here I have a function. I'm inputting the number of seconds from when I drop it, right? So 0 is when it's the moment we let go of it. And as time progresses, t equals 1 is how high is it 1 second after it falls, and so on and so forth. For instance, h of 0 is equal to, we get 0 for t, is equal to 490. H of 10 is easy enough to compute, negative 4.9 times 10 squared, or times 100 plus 490 is equal to 0, right? So this is indicating to us that at the beginning of this, the object is in 490, like I said, 490 meters. And after 10 seconds, it hits the ground, right? H of 10 is 0, so now it's on the ground. So here's a good question to help illustrate this idea of instantaneous rate of change. How fast is that thing moving when it hits the ground, right? So that thing hits the ground, it touches, makes first contact with the ground at some moment, right? At least in theory, the way we're imagining it, it happens in an instant. There's not a change. There's not more than one moment in which it hits time. So there's not a change in time at that moment, and there's not a change in distance. It's at the ground, right? We're just talking about that moment it hits the ground, not when it starts to depress the ground, not when it's bounced back, not any of those other things. Just the moment it hit, how fast is it moving? We know it has a speed. Right? I mean, it doesn't suddenly just not have a speed because of the fact that we're thinking about it at that moment. And yet, our rate of change, our speed formula is broken. It can't handle this because that delta t becomes a 0 in the denominator, right? And in fact, the numerator becomes 0 because there's no change in distance. 0 over 0 is undefined. We don't know how to make sense of that, right? So this is the problem we want to start investigating. So here's how we can do it. At least here's how we can start getting some ideas. Let's imagine we're just trying to do this problem, right? Maybe we're developing a product and it needs to be dropped from 490 meters for some reason, not just because it made these numbers simple for me. We might want to know how fast it is, how fast it's moving, what its velocity is when it impacts the ground. Right? We need to know if it's going to break. We need to know what it's going to do to the ground, all those kinds of things, right? So its velocity would be a good piece of information to have. So one thing I could do is I could think about the average speed, right? Over the whole interval. So instead of thinking how fast is it when it hits the ground, maybe just go, well, you know, how fast was it moving over this entire period? In other words, if we want to figure out the average speed, or let's say velocity. Velocity has direction as well as magnitude. So what I mean by that is it's not just how fast you're moving, but in what direction. In this case, up is positive, down is negative. Average velocity is the final position. Well, let's go back one step. Let's call it the change, like we set up here. It's going to be our change in distance over the change in time. Well, we know the change in distance is our final position minus the initial position. Change in time is the final time minus the initial time. So for this problem, the final position is its height at 10 seconds minus its initial position, its height at 0 seconds. And the change in time is, well, the final time is that 10 seconds minus 0. And what do we get? Well, we know h of 10 is 0. Minus h of 0 is 490, right? We just computed both of these, and then we get over 10. So we get negative 490 over 10, or negative 49. Let's throw some units in there. We get meters in the numerator and seconds in the denominator, so meters per second. Okay, so on average, right, it traveled 490 meters in 10 seconds. That's an average of 49 meters per second. No big surprise there. But then it might occur to us, as we're trying to figure out how hard this thing is going to hit the ground, that this might not be a great average, right? I know when I drop this thing, it starts out moving at no speed. And I know when it hits the ground, it's moving at faster than 0, right? So its speed appears to be increasing, right? All of our intuition tells us this, that if we jump off of the first step, when we hit the ground, it's not too big of a deal. If we jump off the 5th step, we seem to hit the ground a lot harder, right? The further we fall, the faster we're moving. So in this trip from, here's our ball, right? Starts up here, moves down here. It takes 10 seconds to do this whole trip. It's moving faster by the end, right? So if we were to say, look at where it was after about 5 seconds, maybe it's about here. After 5, so let me mark this with time. This is t equals 0. This is t equals 10. I'm just estimating t equals 5 about right here, right? It's not going to be halfway through because it's moving faster at the end. We can see in those last 5 seconds, it moves a greater distance. It has a greater average speed. So let's compute that average. It should be better. It should be closer to what the speed is at the end. All right, so maybe I need to mark this to note this isn't just the average velocity, it's the average velocity for a given interval. It depends on what interval we choose, right? If I drove from here to Portland and you asked how fast was I driving, I could give you the average for the whole trip. I could give you the average from getting to my house to the highway, right? Which would be probably under 20 miles an hour because sometimes you're stopped and most you're going 25. Then the average on the highway, hopefully there's not traffic and your average might be up over 60, right? Depending on what traffic is like, right? So depending on which part of the trip you look at, your average could be much different. So let's add some notation here for the size of this interval. All of the intervals I'm going to look at are going to end at 10 seconds. So I just need to know how big each interval is. So this was the interval over 10 seconds, the full trip. If we look at the interval from 5 seconds till the end of the trip, we're just looking at an interval of 5 seconds, right? And in this case, we're going to do h of 10 minus h of 5 over 10 minus 5, right? So that's the final position is still at the bottom at the end of this. But my initial position, I'm just looking at the second half time-wise of the trip. And I won't go through all the computations. This is an easy enough thing to compute. H of 5 can be plugged into this. And what it works out to be is negative 73.5 meters per second. All right, that negative is because we're traveling down. Remember, it's a velocity, it has a direction. So this is a much different average than the average in the beginning of the trip. Right, and this bears out. You can look at there's plenty of images out there of say photos taken of a ball falling down at regular intervals, and you see that in the beginning it travels very short distance. In the end, it starts to travel greater distances. So now we think to ourselves, all right, this is a better average. Why don't we do even better? Why don't we just look at the last second from finishing at h10, still h of 10, the 10th second of our trip, but starting at the 9th second. So we just look at the last second of the trip, right? Just how fast was it going between the moment of impact and 1 second before that moment. And so our change in time is just 1 second. This can be worked out to be negative 93.1 meters per second. So by the end, in that last second, it's traveling much further. And we can go on and on. Let's do 2 more. Let's look at 100th of a second. This is, right, just looking at the very last moment. 1/100th of a second, and we end up with negative 97 point, where did you go? 95, call it 95 meters per second. And we'll do one more. I have tenths, hundredths, thousandths, 10 thousandths, 1/100th thousandth of a second. I think I got enough nines there. I'm having trouble counting on the screen, and we've got 10 minus 9.99999. And when we do this, we get negative 97.99995 meters per second. Okay, so this is a pretty good estimate, right? We don't imagine, our intuition tells us that in that last 1/100,000th of a second, there's not that much change in speed. Of course, that much change in speed is all dependent on what it is you're doing, right? If you're a physicist working with subatomic particles, 1/100th of a second might be an eternity. And so it's hard to say whether we've gone far enough, if we've gotten a close enough average to what this thing is, right? So depending on what we're doing with our product, maybe this is just fine. But something else is happening here that you've probably noticed, right? We could keep doing this further and further. And if you're curious, you might compute some values for smaller and smaller intervals. And as far as you can take it, whatever the precision of your calculator, sometimes you go too far and your calculator starts rounding. But these numbers will, and as they appear to be doing here, appear to be getting closer and closer to 98 meters per second. Now, I throw a question mark on there because I don't know for sure if that's what's happening, right? Maybe if I did it out to, maybe if I put 10 zeros in there and a 1, all of a sudden I'd see that, oh wait, we just got past 98, right? I did a few with maybe 4 or 5 more zeros and I still just had a string of 97.9999 out to something. But I don't know for sure, right? I don't know when I've gone far enough. So I have to put a question mark here, okay? This idea though, where we're heading at these smaller and smaller intervals, this is the idea of instantaneous rate of change, okay? This is what we're talking about to some extent. We've still got some more structure to add and some more ideas to add. Let's put this on hold for a second and look at what turns out to be a similar idea. You may have noticed when we were computing these average rates of change, there might be something familiar about that formula, right? You might be reminded of slope, right? Slope has the formula, so let's be more careful. The slope of a line is given by, if you have 2 points on the line, you subtract the y coordinates to get the change in y. You subtract the x coordinates to get the change in x. Right? This may be familiar to you that you can write this as delta y over delta x, right? That looks very, very, very much like the slope of a line, or this is the slope of a line, sorry. What we had up here looks very much like the slope of a line. But what line is it the slope of? Well, let's take a look at the graph of this. This red line is the curve h of t, right? That's our h of t. Sorry about that. I keep hitting my hot corners. There we go. Make it a little bigger. So that red line is the curve h of t. The black line is the line we're taking the slope of. So what I mean by that is, like right now, this is our, if we look at the first average speed we computed, right? We could think of this as computing the slope between the points 0, h of 10, and 10, h of 0, right? And that's exactly what this point right here is. This is the point 0, 490, which is h of 10. And this is the point 10, 0, which is h of 0. And so that average speed we computed is the slope of the line connecting those 2 points on the graph, right? Now the graph isn't actually a line. The graph shows us that the speed increases as we go. If you look at this graph, right, as we move forward in time along the horizontal axis, the height changes less in the beginning, right? If you look at the top of that graph, it's almost flat. By the time we get to the right side of the graph near the point at 10, the graph is nearly vertical, right? And so it's going, for each change in X, we're getting more change in Y. And we explored this idea by changing which interval we looked at. So now, instead of doing the interval from 10 seconds to 0 seconds, we looked at the interval from 5 seconds. So I can't stop on 5, that's 4.97, but pretty close. And we see we get a different slope, a different average speed by looking at this, what we call a secant line, the slope of this secant line, right? It's this slope connecting these 2 points on the graph. Notice how much more similar the graph and the line are here, right? We can see there's a lot of difference between the graph and the line out here. In here, the lines and the graph, the curve is they're more similar to each other. And then we increased our, or decreased the size of the interval. So I've got up here a little slider for how big that is. Here's the last second of our trip. And now we see that the line and, sorry, I'm trying to clear all this stuff I wrote on here. We see that the line, the interval, the line between the 2 points at the endpoints of the interval and the graph itself are very similar. If I zoom in a little bit, you see they're not quite the same, but they are quite similar. Let's look at one more. Let's go down to a 1/10, right? And now we see they're incredibly similar, right? Even zoomed in this much, we don't see the difference. So what I've got going on here is I've programmed it to draw this secant line given the 2 points that we chose for our intervals, or whatever size interval I want. But something happens if I try to choose an interval of 0, right? It disappeared because the computer doesn't know, because suddenly what to do, there's suddenly a 0 in the denominator, right? That we would see in those computations we did. Because a size 0 interval would mean we're doing h of 10. So if we do the average size 0 interval, we would do h of 10 minus h of 10 over 10 minus 10, which is 0 over 0, which is not defined. Right? So there's our problem, and now we see it in a geometric way, right? That it's also the slope of these secant lines, right? We also might note, right, as we approach this point, it appears to be getting closer and closer to some line right before it disappears, right? It changes a lot in the beginning, and as we get closer, it seems like it's sort of honing in on some line that it wants to be. It wants to be this line, but then it disappears, okay? Let's explore this idea a little more. Let's use a slightly simpler function and explore this geometric idea a little bit further. What we're looking at here, what the idea we're getting at is, so we started out with instantaneous rate of change. And now we're going to move to what we call the tangent line, right? And the connection is what I just showed you, that when we do an instantaneous rate of change, we're looking at average rates of change. And as we compute more and more of them, it seems like they're getting towards some number, right? Well, the tangent line, the metaphor here is, instead of average rates of change, we're computing or finding lines, slopes of lines that are secant to the graph through 2 different points on the graph. And the tangent line is the line that appears to be coming out as we get those two lines closer and closer together, equivalent to taking smaller and smaller intervals, but we can't get to the point where we have a single point because computing the slope of a line with 1 point is impossible. If there's only 1 point, how do we compute the slope? You get zeros in the numerator and the denominator, right? So this is our issue. And it's the same kind of idea, okay? So let's talk a little bit about this idea. So this tangent line is going to be the line with the slope that's equivalent to this instantaneous rate of change that we're talking about, okay? We're talking in bigger picture right now, into a little bit of intuition, I hope. And so if you leave this video feeling like you don't really know how to do anything, that's not the goal. We want to just connect some ideas right now, throw some pictures in our heads, because we'll explore the details as we move forward. So this tangent line is going to be this line whose slope, it's going to hit the graph right at the point where we're trying to find the instantaneous rate, or the tangent line. And it feels like we want to say it's the point that hits the line, hits the graph. Sorry, it feels like we want to say the tangent line is the line that hits the graph at just 1 point. And if you've heard about tangent lines before, it might be a way in which you've thought about it, right? So if I'm trying to find the tangent line right there, if I think I want to find the line that hits this graph at 1 point, that's a problem, because lots of lines hit this graph at 1 point, right? Every line I'm drawing right now, whoops, that one was pretty bad, right? All these lines hit our graph at 1 point, but none of them feel like what we were just talking about, right? That picture. So a better thought is it's the line that looks the most like our graph at this point, right? Remember when I zoomed in a minute ago, right? If we zoom in on just this little box, we can zoom in a bit. We can't zoom in as much here. I don't know why it doesn't let me adjust. Oh, there we go. Right. So we can zoom in a bit. You can see these graphs look a little bit similar. It's hard to see on this, right? Obviously, I'm just drawing this by hand. But that's the idea, that this graph, this tangent line, is the line that looks like this graph the most right there, right? And if you notice, oops, if you notice, this line I've drawn, oops, doesn't even intersect the graph in only 1 point. It hits it somewhere else. So the idea of 1 point isn't really the crucial idea. The crucial idea is it looks the most like our graph right there. Okay, so let's get at this tangent line a little bit more. Let's look at a function. Let's look at f of x equals x squared. The idea is the same as we use for the instantaneous rate of change. I don't know how to find the slope of a line at 1 point. So why don't I approximate it by finding the slope of the line at 1 point and 1 point pretty close to it, right? If I look at one that's further away, I get an okay approximation, and the closer I make that point together to the one I'm interested in, the better an approximation I get to this idea of the tangent line. Okay, so we want to find, for this function, find the slope of the tangent line at 1, 1, right? This is equivalent to saying find the instantaneous rate of change for this function at that point, okay? So what we'll do, let's look at a sketch. We'll do this with a graph with a nice computer program in a second, but for the moment, let's just deal with my poor sketching. So x squared, y equals, or f of x equals x squared is a parabola. I'll put 1, 1 right here. So the idea is we're going to take, this is the point we care about, we're going to look at another point nearby and write the equation. We're going to find the slope of this line and write the equation for this line through these 2 points. And if we can make this point closer, we'll get a better approximation to the tangent line. So I'm going to write this symbolically. I want a point that's near x equals 1, right? So instead of writing a number, I'm going to write it's 1 plus something, h. I'm just using h to mean some little amount, right? That makes this point up here 1 plus h, f of 1 plus h. Okay, so let's find the slope of this line that I've just sketched. This is our approximating line, okay? So our slope is going to be, so we take that second point, the y coordinate, subtract f of 1, and we take the x coordinate minus the x coordinate of the first point, right? So I'm just finding the slope between these 2 points. That's all I'm doing here, right? And we know a little bit here, 1 plus h, we could put that into x squared. I'm not worried about that right now. F of 1 we know is 1. If we look at our denominator, we've got a positive 1 and a negative 1. All that's left is that h, right? This gives us the slope of this approximating secant line, approximating the tangent line. What do we want to do? We want to make h smaller and smaller and smaller. We have a problem if we let h become 0. If h is 0, we have f of 1 minus 1 or 1 minus 1 over 0. 0 over 0 is undefined. But if we make h small, we will get better and better approximations. And we can write the equation of the tangent line, sorry, the approximating tangent line. So I'll just use this. The tangent line is approximately, I'm going to use the point slope form. If you forget, it's y minus the y coordinate equals m x minus the x coordinate. So for us, the y coordinate, sorry, let me write this better. I'm going to write it as the approximate tangent line. We'll get y minus the y coordinate, f of 1, is equal to m x minus the x coordinate, which is 1, right? That's the point where we want this line to exist. We know what f of 1 is 1. We know what m is. We have it written down right here. We get f of 1 plus h minus 1 over h times x minus 1. Okay, this would give us an the approximate tangent line to this graph. And we can put in values for h. If I put in h equals 10, I get a pretty bad approximating line, right? I'd be going up to x of 11 would be 121. So I'd get some approximating tangent line that would be going way off the screen. But if I make h small, like a 10th or 100th or 1,000th, I'm getting a very good approximation to this thing. Let's look at a much better picture of this whole thing. So here is, there we go. Here's that y equals x squared graph. If you look at what I've got over here, it's what I worked it out with a little more detail, I guess. But this is essentially what we just talked about, the tangent line. I've programmed that in depending on my choice of h. So here is the choice of h equals 2. Notice here's the 0.11. When h is equal to 2, we get x plus h, or x plus 2 is a 3, and then 3 squared is 9. It's the 0.39. If I make h smaller, right, this secant line gets closer and closer to what we imagine the approximating, this approximating secant line gets closer and closer to what we imagine the tangent line to be. But as soon as I try to make h equals 0, the computer stops producing a line because I have an h in the denominator, right? We saw that in the slope, we had an h in the denominator. Also notice I can have h be negative, right? So here I have h equals -3, so I'm starting these approximating secant lines from the other side, and they also appear to go towards this same line, right? They're getting to be better and better approximations of this line. We want to be able to figure out exactly what that line is. I already know how to do that. I'm gonna draw that line in, And notice what happens as we get closer and closer to that line, right? Sorry, as h gets smaller and smaller, the green line becomes, let's zoom in a bit. As h gets closer and closer to 0, the green line gets closer and closer to that black line. It can't quite be it. Here's h equals 0, the green line disappears, the computer doesn't know what to do with the 0 in the denominator. And the same thing from the other side. As h gets closer to 0, that green line gets really close to that black line, okay? Also notice how similar the graph of x squared and the graph of this tangent line are at this point, right? You can see on the edges of the screen right now that the red line curves just a little bit off that black line. And if I keep, oops, wrong way. If I keep zooming in, the difference becomes even more negligible, right? Closer to that point. So right now, if you look at the scale, we're looking at 10 thousandths of a unit, right? Is like our units along the x-axis. We're looking very close and we can't see any difference between these two things, okay? So this is the problem we want to figure out, right? How did I know to jump to this line 2x minus 1? We're not going to figure that out right now. What we're going to do in the next few videos, and this is the heart of what we call differential calculus. This is the first part of calculus where we're trying to solve this problem of instantaneous rate of change. What we want to solve, our core problem is, how do we find this slope when h is 0? How do we find the slope of the tangent line when h equals 0, right? Where h here is the difference between the x coordinates. In other words, when there's no difference, when we've slid the other point on that secant line right on top of our point and our computer makes it disappear, how do we not have that disappear, right? That's what we want to get at. The tool we're going to use to do this, we're going to use something called limits, okay? Limits are, I mean, there's going to be a whole bunch of detail around this, but our first idea of limits is, can we formalize what we saw in those first computations? That these numbers, for instance, of this average speed of our marble dropping was getting closer and closer and closer to 98. Can we show that it actually is going to keep getting closer? That I'm never going to go down to 0.00000001 and all of a sudden it's going to jump over 98. Do I know that it's actually going to 98? This idea of going towards. There's no number I can put in to make this computation equal 98, but can I show that it's always going to be going closer and closer? I can make it as close as I want to 98 by making my interval smaller and smaller and smaller, right? That's the idea of the limit. Graphically, we saw it when we looked at these secant lines getting closer and closer to that tangent line. They disappear at 0. We can't make them get there, but at least up to the resolution of this computer, we can get them incredibly close together, right? And I could keep getting it closer together if I had a more powerful computer, right? This is the idea of limits, that we can talk about something that approaches something even if it can't quite get there, right? Obviously, we need more more detail than that, which we'll do later. We're going to use these limits to find the slope of the tangent line. And we're going to call this thing the derivative. And this mathematical object, the derivative, is really what we're talking about in Calc 1. This is what we're called differential calculus. What is this, the derivative, okay? And that's the idea we're going to explore. So we're starting with this instantaneous rate of change problem, which is equivalent to this tangent line problem. And we're going to use something called the limits to find these numbers, right? To find the slope of the tangent line, to find the instantaneous rate of change. And we're going to call this solution the derivative. That's where we're headed. We'll do more in the next one. Thanks, everybody. I will see you next time.